Hello, students. We're going to wrap up our discussion of Chapter 12, Kinetics. I just want to go back through in a little more detail something about activation energy and also a little bit on catalysis. So this is actually just a recap of the beginning of 12.6 and the very beginning of 12.7. So recall that molecules are in motion. That's kinetic um, collision model, that molecules are in motion, they collide to make product. To make product, though, they have to have effective collisions. We saw that it's harder for them to make product when the activation energy is very high. It's easier and faster for them to make product when the activation energies are lower. What this video lecture is just going to go through, and it's fairly brief, is just the idea of what a transition state is. So, and also to show you some energy diagrams that you're going to see in almost all of the remainder of your chemistry classes. So these energy diagrams I think are super important. Okay, so this is a reaction of BrCH3 plus hydroxide to make Br minus and methanol CH3OH. This is showing that there's a transition state between products and reactants. Now, see, normally hold up. Normally, carbon just has 4 bonds. So here's the H's. And then here's the Br. So that would be this one. But you notice how the hydroxide's coming in here. And there's this intermediate where the bond is breaking between the C and the Br and forming between the C and the OH. And so this is very unstable because carbon prefers 4 bonds. So it's like an intermediate between product and reactants, but there's definitely a lot of instability here. So let's take a look at what that would look like on an energy diagram. That particular picture we just saw is this one here in the center. And that would be here, the transition state up at the top of this energy diagram. Here's our reactants. And here's our product. And then there's this activation energy, right? That's required to reach that transition state. Then once those molecules exceed that energy, then they start to form product. You get back more energy than you put in. So if you notice, our overall energy change here is negative and exothermic. Now, the part that I just wanted to share with you is that if a reaction is giving off a lot of heat, then what's going to happen is that to try to reverse it, so to go from products back to reactants, is this line here. Do you notice that? That would be the activation energy of the reverse reaction. And that's very high here because this was exothermic. Okay, so to give you an impression of that concept, let's take a look at a couple more diagrams and then we'll do a problem. So here, this second picture, I'm going to highlight it in yellow. Here is our reactants and products. You see how the overall energy change is negative. It's dropping in energy. So this guy is exothermic. You see how there's a forward reaction, activation energy. So here's our forward reaction, activation energy to reach that transition state. But then once those molecules exceed activation energy, they release that energy and more because it's exothermic. Now to go reverse, though, the activation energy is very high. So the E of A reverse is much greater than E of A forward in an exothermic process. Okay, the first diagram's the other way around, which is that this is a reaction that's endothermic, heat requiring. So it requires, there's a very large activation energy going forward. You get some of it back, but you still have this net energy you have to put in. So the activation energy forward is much greater than the activation energy in the reverse process for an endothermic. Heat's required there, right, to get that process. But you notice a very, very large forward activation energy because it's from here all the way up to the transition state. Okay, let's practice a problem real quick. Here's a key reaction in the upper atmosphere. E of A forward is 19 kilojoules. Delta H of reaction is negative 392. Draw a reaction energy diagram. I'm going to cross off predict a structure for the transition state. Just know that it's that partial bond breaking, bonds forming. And we'll calculate E of A of reverse. So why don't you go ahead and pause me and try this problem and then check your answer. Okay, so here's our energy diagram. It's exothermic. Our reactants are ozone plus oxygen, and then our product is 2 oxygen gas. So our overall energy change is from here to here. That delta H is negative 392 kilojoules. It has 19 kilojoules for its activation energy to reach that transition state. And that would be here, E of A plus 19. I know I crossed off predict a structure, but here's ozone structure. And you're adding an O atom. So the transition state's going to be sort of that middle point between where this bond forms and it breaks off, right? There's going to be somewhere in that middle area, gray area of that. And then lastly, it's asking us what's activation energy for the reverse. So notice for the reverse, we have to go up all the way to that transition state here. That was not a very well drawn. I think I'll erase that. I'll just use a different color pen. That didn't work, did it? So from here up to the top, that's going to be E of A reverse. And the picture's great because it really helps us to realize that I'm going to have to add that 392, put that in, plus the 19. So if a process is exothermic, its reverse activation energy is very high. And here's a prettier picture. Okay, this says to use this formula. I actually would say if you draw the pic, it's easy to see that you're taking a positive 392 and adding it to the 19. That's the whole point of the graphic, is to help visualize that. Okay, so I'm not a big fan of the equation up here at the top. Okay. Okay, your book has a fairly lengthy discussion of catalysts in 12.7. Now, as a biochemist, I love talking about catalysts. It's a whole thing in biochemistry. But I want you to know that in your textbook, I would probably read page 500 The rest of it you can read, but it's really just giving you very specific examples of catalysis. I love the part about at the end, there's a great box called Chemical Connections. Called enzymes. And if you read that, if you're interested, that's our biochem example. And I do really like that. But I just won't lecture on that part. Okay. But if you want to make a connection to something, I guess you'd say a little more interesting from a biology or biochemistry example, then read that section. But basically, a catalyst, going back to our E of A diagram. So if we have product and reactant, a catalyst job is to lower activation energy. So here is a different transition state. So the transition state with a catalyst, E of A is lowered. The transition state without the catalyst is higher energy. So it's up here at the top. Okay, so transition state with the catalyst has a lower activation energy. And so that's the whole point of a catalyst. Now, the reason why I want to end with this is this ties into our mechanism. So we talked about mechanisms, and basically the idea is this, that the enzyme in, let's say, biochem or catalyst. Sorry, I teach biochemistry, so I'm just going to say the word enzyme instead. So that's the biochemical catalyst. There's other catalysts. Your book has examples of more industrial catalysts. But the idea is this, that there's an alternative mechanism. And in the alternative mechanism, the slow step, right, that's the rate limiting, has a lower E of A. Whereas without the catalyst, you're looking at a mechanism whose slow step has a higher activation energy. And so then it's slower. And so catalysts are the only way that we lower activation energy, not temperature changes. And they play a huge role in industrial chemistry and in biochemistry. So the processes in the body, for example, to process glucose for energy, we have to have catalysts to speed up those chemical changes. If not, they just wouldn't happen at the speed that we need them to. Okay, they tend to be more unfavorable. The activation energies would be too high. Okay, and with that, I'm just going to wrap that up. Let me know if you have questions.